this is my redstone computer that I created when I was on holiday because I had not much else to do because I was on so many friggin' long haul flights. I hate those things, but at least it gives me plenty of time to build this. This represents probably about 20 hours of work, so actually it's not all that bad compared to some things. Hermitcraft, especially Psycraft, is much worse. Like, people will just spend so much time on Psycraft. Anyway, I digress, I think is the statement. It's a very simple computer with 3 registers. This one here is the C register. This one, well, 3 general purpose registers. That's the C register, that's the A register, that's the B register. It has several other registers, such as the temp register, which is useful for add immediate instructions. The program counter, which is that one, the black one, and the memory address register, which is this one here, the pink. And you can see it's kind of different to normal redstone computers in that the bus is done vertically. And actually that worked out so well because it's much easier to make 2 wide tileable vertically tileable than 2 wide tileable horizontally tileable, or it would even have to be probably 1 wide tileable. No, 2 wide tileable. Anyway, it's a lot easier to do that, so it allowed a lot more compactness because the bulk of the computer is on this side of the bus. And just this stuff here. That is most of the computer. The only things that it is not is this entire huge thing here, which is just the instruction decoder. The reason it has to be so big is I decided to add a ridiculous number of instructions. You can see, actually these aren't really, these are programmed but not tested. But I don't know how many instructions there are. Well, it will probably be somewhere. No, I didn't do a linear naming scheme. I did something a bit more intuitive, or actually less intuitive, but anyway, it's got a lot of instructions, and each of them obviously needs 1 to 4 of these lines. Each of these represent one a thing to do every clock cycle. So the first 2 obviously don't correspond to an instruction because they're fetch and decode basically. And wherever there's a gold block and a repeater, it will trigger that line. And so this one, for example, is PC in, and then this is the fetch decode, so the fetch cycle. So program counter in, memory address register in, ALU input 1, and I'll come to that in a minute. ALU input PC, also I'll come to in a minute, and then ALU out. So basically increment the program counter. And yeah, so that explains why this thing is so huge. And the other huge thing is the memory, because you can't really build vertical memory. So just a lot of the space is just spent in converting the vertical signals to horizontal signals, which I've done a bit of trickery in, especially over here. That looks horrible. But currently it has, I think, 8 bytes of RAM. 1, 2, 3, 4, 5, no, 16 bytes of RAM. I'm an idiot. And that's the most significant bit. That's the least significant bit in case I forget, which I have forgotten several times. Over here, I mixed up the most significant bit and the least significant bit while programming this entire huge thing, because it takes the 4 T states and then 2 the 0 flag and the carry flag to tell it which one of these to do, basically. And also it takes the address lines underneath. I'm making no sense probably, but anyway. This is expandable up to 256 bytes, but I just haven't been bothered to do it because there's not really much of a need with a computer this simple. And ALU actually is quite a tricky thing to build. This is not the best ALU design, but because I was offline for most of the time where I was building this, I couldn't look up a better ALU design, and I couldn't be bothered to design one from scratch because that often goes really badly. Although I did design the registers from scratch, however, that came with its own problems, such as the fact that I built the first few wrong and they had bugs that caused everything to break, so I had to retrofit them. But I think by the end, the C register was built last, and this is a pretty good 2 high tileable register design. Yeah, it takes in a not output enable though, which is what caused quite a lot of headaches, rather than a normal active high output enable. It's an active low output enable. Anyway, the ALU input things that I was talking about before, each side of the ALU, this side corresponds to the B input, I think, I don't know, and this side corresponds to the A input. Maybe the other way around, it doesn't really matter. But each side, as you can see, this side is hooked up to the A register, this side is hooked up to the PC, and, well, the A register and the PC. And I've made it so that you can switch between using them. And to save on instruction or microcode word bits, I don't know how to explain that, but I've made it default to one register. It defaults to the A register being the input of the ALU. And only if I tell it to make the PC the input of the ALU will it make the PC the input of the ALU. And same goes for over here, except there are, I think, 3 inputs here instead of just 2. Yeah, so it gets a bit more complex because it has the B register, the temp register, which is used in immediate additions, because I load in a data value from memory into the temp register, and then obviously you can only then do an immediate logic operation with the A register as opposed to with the B register as well. But I think it's a simple CPU. It's in Minecraft, for goodness sake. So yeah, the wiring was a bit complex to get because there's not awfully much space down here. I had to do some trickery with trying to fit it in and moving bits of the components around. So yeah, you can generate a 1, you can put the temp register, or you can put the B register on this side of the ALU. But there's this huge block of stuff, which is basically it's an XOR gate. It takes what would go straight into the ALU and XORs it with a value. And that basically also, that value is also fed into the carry input of the first adder module. This allows for 2's complement subtraction. So basically, why is that on? That's weird. Bugs when moving worlds between versions. Anyway, that allows for subtraction as well, which is very useful. And I believe this computer is Turing complete because it does support the carry and 0 flags. Apparently I've only built one of them. No, yeah, what? No, the other one's just located down here. Yes, that would make sense. It just comes out of the carry output and there's a control line to control whether it should actually latch the carry output or not. Because if you're doing an add 1 to the PC, then you don't want it to latch the carry output, otherwise you're in a bit of a problem. But yeah, each of the microcode wiring is a bit of a mess because I thought, oh, I'll make it a standard level, so I made it at this level, but then this line got out of sync somehow, and then this line is too low, and then it's a nightmare. Anyway, what else is there to say about this? It runs on a clock speed of slow. I think it is it's a 20, should be a 20 item clock. It can actually go slower than that. But faster rather than that. Of course it can go slower. But I haven't really tested it extensively. This basically says that this pulse extender makes the clock stay on for longer than it is off, because it doesn't need to be off for as long as it is on, because when the clock goes high, everything like the ALU starts calculating, and the ALU is the slowest bit because obviously it's a ripple carry all the way down. And yeah, I've had to stagger the ALU modules obviously because they're not one or too high tileable. And when the clock goes low, it only needs to latch the output that's on the bus into any registers. So that obviously takes a very short amount of time. I think it only takes a couple of ticks. So you need a long time for it to be on for the ALU to calculate stuff, but then you only need it to be low for a short amount of time to latch the output. Obviously this is ROM as well, so I currently don't have a RAM in function because it's ROM. Anyway, I shall load up a program and run it and hopefully understand what's going on. If I don't understand what's going on, then I've made a mistake. Anyway, you have to press all of these three in succession to reset everything, and then wait, because there's basically a clock over here that has to finish clocking itself to reset the ring counter for the T states. I think it's finished, it's fine. Then I shall... It's basically self-documenting as well, because you can go over here and look at which things are which. So what should I do? Should I do like a 10 add 5? Yeah, I think I'll do a 10 add 5 and put the 5 in the A register. So I will have over here somewhere will be all the jump instructions I haven't actually tested, but I think they should be fine. So I'm not going to use a jump instruction because I haven't tested them. Maybe I'll get round to it in the future. But you just basically look along here and you say move start A. That's a 1 and then all zeros. So you go over to the memory and I've already got that programmed in. You put a torch where there's supposed to be a 1 and no torch when there's supposed to be a 0. Anyway, I'll speed through this to save your sanity. So I've programmed in a program, add, move the number 5, move the number 10 rather, to A, and then move the number 5 to B, and then add B to A. So hopefully in the A register we will see 15, or 1111 in binary. I've already reset it, so I can just start the clock, and wait basically and hope that it hasn't broken anything by being changed versions. But yeah, this is the program counter, this is the A register. I'm gonna look at them, and that's the lights over here are the bus, and I'll probably speed through this because it takes a while, not like ages, but a lot longer than your CPU takes to do it. There we go. It's handed over control to the program counter now because that light's on. That light means that ALU is feeding the the A register is feeding the ALU, and that light means the B register is feeding I can't speak. The PC register is feeding the ALU. Anyway, yes, I shall speed through this. So as you can see, there is currently a 15, sorry, in the A register, which means it has worked. It has added 5 and 10, and it just increments to the next memory address where it will just find all zeros, which is a no-op, so it will just do nothing. So I'll go and stop the clock, and yeah, hopefully that time lapse looked cool. I quite like seeing all the redstone flashing on and off. But yeah, that's probably about it. If I remember, I'll put a world download in the description in case anyone kind of likes this sort of thing. If I don't remember, bug me about it in the comments and I'll try and edit the video, or edit the description rather, because the chances are I will probably forget. But it also makes for quite a good parkour course, if you like parkour, because you can sort of, I don't know. There's a way. If you can get into the ALU, then you're sorted, because it goes like stepwise upwards. But getting into the ALU is sometimes a bit of a challenge, because everything's vertical. You can't really get inside any of this. So you have to basically rely on the ALU and these white wires and other sort of random wires. I think I might be able to get in from here. It's so close. Even closer. Anyway, yeah, if you like parkour, then you can try and get from the lowest bit to the highest bit. No, it doesn't lead me to the ALU. Well, quite. Yes, I know I just cheated there. But yeah, I don't know. Could be a fun challenge. Or maybe you just want to check out how it's done, really, because I don't honestly know myself. And on that note, goodbye.